lecture number 9. This one will be on describing or summarizing univariate data. I'll have a separate lecture when we get to the Pearson product moment correlation coefficient on bivariate data. But for now, we're dealing with just one variable at a time. So I will briefly go over the techniques for describing univariate data. We will go in more detail in subsequent lectures and focus on the measures of center, the measures of dispersion, and measures of shape, skewness, and kurtosis. Now you notice I put a little asterisk next to the mean, and that's because there's actually multiple means. In this class, we will only cover the arithmetic mean and the overall or weighted mean. But just keep in mind there are other means like the geometric mean and the harmonic mean. So this is what this lecture will cover. We will add detail to the measures of central tendency, measures of dispersion, and measures of shape in subsequent lectures. So this one's just an overview. So it's going to be pretty short. So 4 ways to describe or summarize univariate data. So in other words, we have some data, and with a single value, how can we describe or summarize that data set? And so we've got the measures of center, and the measures of center or central tendency try to provide us with one number that best describes the data set as a whole. And you're probably familiar with the mean. The mean is the most common measure of center, but it's not the only measure of center. Okay. Then we have the measures of dispersion, sometimes called the measures of variability. They give us a measure of how spread or varied our data are, typically about the mean, but not always. So for example, we could have a data set of 2, 2, and 2. Well, the mean for 2, 2, and 2 would be, you got it, 2. What if I gave you a data set of 1, 2, and 3? Well, again, the mean would also be 2, but you could see the data set now from going from 2, 2, and 2 to 1, 2, and 3. The second data set has a little bit more spread to it. It's a little bit more varied. And if I went to 0, 2, and 4, well, that has even more variability, more spread than 1, 2, and 3, or 2, 2, and 2, even though they all have the same measure of center. So the measures of dispersion give us a measure of spread. They complement, they give us something in addition to the measures of center. And then we have measures of shape. And they come in 2 flavors. Measures of symmetry, which are skewness, or measures of skewness, which provide us some information about how symmetrical our data set happens to be. And then the measures of kurtosis, probably a term you've never heard of, and that tells us how flat or steep our data are relative to a normal distribution. That's why I put a little asterisk there. It's not an absolute flatness or steepness, it's a relative to a normal distribution. So we can have a single number that gives us the one number that best describes our data set. We can choose a way to describe our data set in terms of how spread out our data happen to be, how much variation there is. And when we look at the shape, how symmetrical our data are, and relative to normal curve, the bell curve, how flat or steep our data happen to be. So I have tried, I know it's a little bit busy, but to give you a little table with the most popular measures. And the first thing that you're going to notice is that the measures of central tendency and the measures of dispersion, I put them in different colors. So this type of green here versus these 2 measures of shape. And the reason for that is because each of these, the arithmetic mean, weighted mean, median, mode, range, interquartile range, etc., all of these over here, each of these is a specific formula, a specific technique for computing a value that gives us a measure of center or a measure of dispersion. These over here aren't separate techniques. So we don't have a technique for computing symmetry and positive skewness and negative skewness. What we do is just have one technique, and based on the value we get, we can determine, hey, we think our data looks pretty symmetrical. Our data is positively skewed, meaning we have a outlier on the larger side relative to the data, or a right skewed distribution, or we tend to have an outlier or two to the smaller side towards the negative side. But they're not are separate equations like we would for these over here. So it's just one formula, and then based on that value, we can make the determination if it's symmetrical or not. And same with the measures of kurtosis. Uh, Again, we would say, hey, based on the value that we've computed, our data set look fairly normal in terms of peakedness, flatness, steepness relative to a normal curve, or they look a little bit flatter than we expect, or a little bit steeper than we would expect for a normal distribution. Um, and I say we look, but we're actually getting a value that could empirically tell us if it's flatter or steeper than what we would expect for a normal distribution. So just one formula here, one formula here. We're not going to learn how to calculate these in this class. I will show you how to get a value with a statistical program. And I expect you would be able to see a distribution and determine, look at it, tell me if it's symmetrical or not. But we don't actually have to compute these for this class. But I would expect you have a decent understanding of these. We've got the arithmetic mean, and I put the arithmetic mean in quotes because technically it is called the arithmetic mean, the one that we're going to focus on, but it's so commonly used, most people just say the mean. But I put it here to let you know it's not the only mean. We will also cover the weighted mean, which is very useful when we have groups that have different weights, such as a class that has 3 hours of credit versus a 1 hour class. You can't just take your 2 grades in 2 classes and add them up. We have the median or middle number and the mode, and I will discuss these in more details in an upcoming lecture, probably lecture 10. And then we will follow that with these measures of dispersion, the range, interquartile range, standard deviation, variance, and coefficient of variation in the lecture following this one. Just as a quick reference, next to these, I've put the common symbols for these tests. These right here, for example, X bar and mu, or when you come over here and you see sigma squared or sigma, these are the statistical symbols, but as you can see, they're special symbols. They're hard to find, hard to insert sometimes, depending on how familiar you are. APA, and that's the format we will use in this class, just says, hey, let's put a capital italicized M for mean rather than using X bar or mu. Let's do SD italicized for standard deviation rather than sigma or little s. Much easier to type. Don't have to worry about inserting special formulas, so forth. So if you're wondering why we have so many, if you remember from one of the previous lectures, we have populations and samples, and populations yield parameters, and samples can give us statistics. And so this would be a statistic. This would be a sample mean, a statistic. This would be a population mean. They're computed the same, and we'll cover that in more detail later. And I will provide this same information later. But that's why in some cases you see 3 rather than just 2. Instead of 1 for the sample and 1 for the population, we have this common APA easy to type symbol. So let's do a few review questions, see how you understand that basic information. The mean is a measure of central tendency. That is true, along with the mode and the median being the most commonly used, mean, median, mode. We also have the arithmetic mean and or the overall mean, weighted mean, but this is true. There are several different measures of central tendency. That's true. I just said the mean, median, mode, etc. And the reason I ask this question is because what if I were to say there are several different measures of this, let's say, kurtosis or skewness? And then that's false. There's outcomes like positively skewed or negatively skewed, but there's just one formula, one test, if you will. So this is true. So here's that very question I was mentioning. There are several different measures of skewness. No, it's false. You only have one formula, one outcome, but based on that outcome, we could say it looks skewed, it looks symmetrical, or this value is telling us it's skewed. This value is telling us it's symmetrical. So the measures of shape really give you more of a continuum where we go from flat to steep or symmetrical to skewed, rather than having different formulas and different approaches to determining skewness or kurtosis. There are several different measures of dispersion. This is absolutely true. We have the standard deviation being the most common. We also have the range and interquartile range, coefficient of variation, the variance. Skewness and dispersion are both measures of shape. Starts off good because skewness is a measure of shape. It tells us something about symmetry, but dispersion, that's a measure of spread. So skewness and kurtosis would make this true. Skewness and dispersion make it false. The range and interquartile range, usually just IQR because that's a mouthful, are both measures of dispersion. And that is absolutely true, along with standard deviation and the variance and the coefficient of variation. Measures of central tendency provide a typical or average number, that one number that tries to best describe the data that you have. And that's what you're trying to do with the measures of central tendency. So that is true. The measures of skewness provide an indicator of how flat or steep the data are. And just as a reminder, it sounds unusual, but data are plural. So it's not data is, but data are. You want to be technical about it, and I do. Right? And so this is false. The reason it's false is because it's the measures of kurtosis that provide us a measure of how flat or steep the data are relative to a normal distribution. Skewness provides a measure or an indicator of symmetry. Measures of dispersion provide an indicator of spread or variability. That's exactly what they do. Those are the range, interquartile range, variance, standard deviation, etc. So true. That's it for this one.